Okay, this is section SD, which represents the similarity and diagonalization. So similarity of matrices is a complex topic, but it basically involves solving this particular equation. If we take a matrix S and take its inverse, and then multiply that by matrix A, and then multiply by matrix S, so it's in that order. The inverse of S times A times S, what we'll end up with is a diagonal matrix. And there are some rules for selecting S, which we'll talk about in just a second, but here's our matrix A. Unfortunately, in order to find matrix S, you need to find the eigenspaces of matrix A, and that of course means determining what its eigenvalues are. And then what will turn out to be the case is this product will produce the diagonal matrix, and that diagonal matrix will have zeros in every element except for the diagonal, and the main diagonal will contain the eigenvalues of this particular matrix. So you can see we're supposed to get 4 eigenvalues for it, and that of course is what we'll get if we follow the formula that we want to find the characteristic polynomial and set it equal to 0, and that of course is going to be a minus lambda I. Well, as you can see, for a 4x4 matrix, this would be a tremendous amount of manual work. We'd have to put minus lambda along each one of the diagonals, and then we'd have to find the determinant. Of course, there are technology tools that can help us. Both your calculator enables you to find eigenvalues, and Wolfram Alpha will actually use the function eigenvalue, and then you go ahead and enter this matrix in, and it'll come back and show you both the characteristic equation, which in our case is lambda minus 3 times lambda minus 2 squared, and lambda plus 1, all equal to 0. So that produces eigenvalues of lambda equals 1, 2, 2, negative 1, 2, 2, or 3. So there's 4 eigenvalues. The negative 1 and 3 both have algebraic multiplicity of 1. The 2 has an algebraic multiplicity of 2, and that means there's 4 eigenvalues. There's supposed to be 4. That means this guy is diagonalizable, because in order to be diagonalizable, all that has to be true is that the sum of the algebraic, no, not the sum, but the algebraic and geometric multiplicities must be the same. And they are. The algebraic multiplicity is 2, and the geometric multiplicity must be greater than or equal to it. And so, less than or equal to it. And so this one's 2. These are both 1, and so we get 4 for the sum of all of them. And so there it is. We can also go one step further, and that is Wolfram Alpha actually has a diagonalize function as well. Just say diagonalize, and again use the same matrix you entered in for eigenvalues, and it's going to come back and tell you what S is. So it will actually determine what the eigenvectors are for each one of these. Now remember, we always want to retain our ability to do these manually. In order to find the eigenvectors of each eigenvalue, I would simply substitute this in. I'd take 18 minus 1, 8 minus 1, negative 16 minus 1, and negative 4 minus 1, and then I would take that matrix and find its null set. And the null set of that matrix would actually be the eigen space for the negative 1 lambda. And then I'd repeat it again for 2. I can tell you once you subtract 2 from, or add 2 to each one of these, you're going to get a null space that contains 2 vectors in it, because the algebraic and geometric multiplicity here is 2. And then you'd sub in 3 and do the same thing. And what you'd end up with is this. This is what S is for this particular, whoops, it's a vector set. Although I'm just going to write it as a matrix. So even though it is a vector set, I'm just going to write it as a matrix. Minus 1, negative 2, 0, and 1. Followed by 0, negative 1, 0, and 1, negative 3, negative 1, 1, and 0, and finally 6, 0, negative 3, and 1. So this would be the S matrix that I would use. These are actually the eigenvectors that correspond to these four values. Two of them come from the 2, one of them from the -1, and one of them from the 3. So these are the total of the eigenspaces of all four eigenvalues. And if I take this and perform this operation, S minus 1, so I'd have to take the inverse of this matrix times matrix A, our original matrix, and then multiply again by S. What I'll end up with is the diagonal matrix, and I can show you what that is too. That contains the eigenvalues along its main diagonal, so -1, 2, 2, and 3, and everywhere else is a 0. So this would be the matrix D. This is the diagonal matrix that corresponds to matrix A. It's the result of the product of these three matrices. It has the eigenvalues along its main diagonal, and of course the matrix S is selected to be the eigenspaces, the total eigenspaces for all of the eigenvectors. And that's it, that's diagonalization. You can see that diagonalizing a matrix has a number of important functions, not the least of which is it's one of the easiest ways to get the eigenvalues is you diagonalize it and then you'll produce the eigenvalues from it. And because it is all just a bunch of complex algebra, utilizing technology to shorten your work is not a problem. But be prepared to do something like this if the matrix were smaller, say a 2x2 or a 3x3, those would not be difficult to perform this manual process on. But once we get to 4x4 and 5x5, it's a little bit like finding reduced row echelon form for the larger matrices. It's so time consuming and tedious that even though we could do this process when given sufficient time, we'd much rather utilize technology to very quickly provide us with the S vector and the D vector. And that's it, that's diagonalization. And remember, diagonalization means what we're finding is a matrix that is similar to the matrix we started with. So A and D then would be similar matrices. And what does it mean that they're similar? It means they have the same eigenvalues, because this set would actually be the eigenvalues of this matrix as well.